So, hello everyone again, this is lecture number 11 part 2 of semiconductor electronics materials devices and simple circuits. In the previous part at the ending we started with the new discussion, that is about digital electronics and logic gates. We understood basically what is the difference between the analog signal and a digital signal. That thing being said, let us start our discussion regarding logic gates and then move forward. So, I am Sameer Lavankar, let us begin our discussion. So, currently we are on the 10th topic, that is digital electronics and logic gates. Let us start the discussion directly. So, these all things are being explained directly, let us move here. Okay. So, logic gates. So, a gate is a digital circuit, please remember it is a digital circuit, okay, that follows certain logical relationship between the input and the output voltages. So, we will try to input some voltages. So, 1 means basically 5 voltages being entering upon, and 0 volts basically can mean 0 voltage entering upon. Now, this 0, if you go much deeper in the sense, 0 is basically referred to the minimum voltage this can happen. So, that can be minus 5 voltage also, because if a sinusoidal wave is being formed, then there will be plus 5 and minus 5. So, sometimes that 0 can also refer to minus 5 voltage also. So, that is depending upon the scenario, but major crux which you need to remember is the maximum is being denoted by 1 and the minimum is denoted by 0. So, therefore, they are generally known as logic gates. Gates because they control the flow of information. So, because depending upon the combination of all the logics which are being, or the inputs which are being entering upon, it depends that which output will flow forward. The 5 common logic gates used are NOT, AND, OR, NAND and NOR. Each logic gate is indicated by a symbol and it is denoted, and its function is defined by a truth table that shows all the possible input logical level combinations with their respective output logic levels. Truth tables help understand the behavior of logic gates. These logic gates can be realized using semiconductor devices. Okay. So, that is how these logic gates are being formed, they are basically formed using semiconductor devices. Fine. So, let us start the first, that is NOT gate. Okay. As a name only suggests, NOT. So, what does the NOT means? NOT basically means that if your input is 0, it will reverse it. If your input is 1, it will reverse it. Okay. So, this is the most basic gate with one input and one output. What does it mean? One input is there and one output is there. It produces a one output if the input is 0 and vice versa. So, what basically it is saying? So, let us suppose a 0 input. So, what can be 0 input? 0 input can be either 0 voltage also, it can be minus 5 voltage also, and what can be output? Output can be basically 1. So, 1 can be anything. So, it is maximum value, it is plus 5 volt depending upon the current which is flowing upon or the voltage which is flowing upon. So, this 0 and 1 basically depict the values, not the exact numbers. So, basically depends the binary number which this gates uses. So, if the input is 0, it will give you output as 1, and if the input is 1, it will give you the output as 0. Fine. That is, it produces an inverted version of the input and its output, and that is why it is also called as inverter. Inverter as in it will just invert the value. Fine. So, if let us suppose final value, let us say just using the logic gates, as in how can we use the logic gates in real life scenario. Let us say what only and only NOT gate has to be utilized, and we know that our A value is let us say 1 only, right, and let us say the final output we require has to be 1, but we need to use the logic gates. Okay. So, if we need to use a logic gate, what we will do? I will first input a NOT gate here directly. So, this is the symbol which is utilized for a NOT gate. So, after one NOT gate, what will I get the answer? I will get the answer as 0, but if I again use a NOT gate, I will get the answer as 1. So, that is how you can use the NOT gates to get to the desirable results. Fine. So, that is one thing. The commonly used symbol together with the truth table for this gate is given in the figure. So, this is basically a truth table for NOT gate. Fine. So, NOT gate is understood. Next is OR gate. So, OR gate is having 2 or more inputs with one output. So, as you can see, 2 minimum inputs are required and only one output will be there. Fine. What is the meaning of OR gate? OR gate simply means that if either one of them is 1, then the answer will be 1. If either of them are not 1, then the answer will be 0. Simple explanation, we will try to understand. So, the logic symbol and the truth table are shown in figure below. The output y is 1, the output y is 1 when either input A or input B or both are 1. when either input A or input B or both are 1. So, I guess this is being understood to you, that is if any of the input is high, high means one number, right, the output is high. So, a simple explanation is here. Apart from carrying out the above mathematical logic operation, this gate can be used for modifying the pulse waveform as explained in the following example. So, before going to the example, let me again use it. Let us suppose finally, for any case scenario we also only want that our answer should be 1, and we can only use, let us suppose, NOT gate and OR gate. So, what we will do, let us suppose first of all we use a, this is A input, this is B input, and this is your OR gate here, correct. Okay. So, now what is happening, let us suppose we know that either of them is 1. So, if either of them is 1, then it is basically sure, it is 100% surety that you will get the answer as 1 only. But let us suppose both are 0. If both are 0 and we already know that both are 0, what we will do? We will just simply add a NOT gate here. If we will add a NOT gate here, what will be the answer? Or either not even required, we need to add NOT gate to the both side. We can only add a NOT gate to one of either of them. So, if let us suppose we add a NOT gate at A position, this 0 will convert to 1, and then finally again you will get answer as 1 only, correct. Acha, one thing more. So, now if we add only a NOT gate here, let us take again all the case scenarios, so that we can understand that can we get the answer as 1 every time. So, let me use one case. Let us say that this was the input, this was, let us say, this like this, and this is how an OR gate was being formed, and this is the output Y. Let us say this is your A input, this is your B input, correct. So, now let me make a truth table here. Okay. So, we are just trying to understand basic different combinations in which this logic gates can be utilized. So, let us say I write A, let us say I write B, and let us say I write Y. Okay. So, if both values are 0 0, what will happen? So, 0 will be here, 0 will be here, it will change it to 1 here and 0 here only, because there is nothing between B, correct. So, 1 0 will give you answer as 1, correct. So, this we got answer. Now, let us try to change the positions or change the values again. So, what will happen with 1 0, 0 1 and 1 1, okay. So, let us try to understand. So, 1 0, so 1 0 will be 1 here, 0 here, right. So, what will happen here? It will simply give you the answer as 0 here and 0 here, which will give you answer as 0, okay. Next thing is 0 1. So, let us say I write this as 0, this as 1, correct. So, this will be 1, this will be 1, which will give you answer as 1 only. And next thing is, let us suppose this is 1, this is 1, this will give you 0, this will give you 1, and that is how you will get the answer as 1, okay. So, that is how a truth table is formed, and that is how different combinations of AND gate or OR gate can be utilized, okay. So, you can see clearly that this is quite different from the OR gate, because in OR gate 0 is only and only obtained when both are 0, but we obtain 0 here when A is 1, okay. So, depending on the scenario which is required, simple these logic gates are being utilized by the engineers, fine. So, now let us look at this example. So, justify the output waveform Y of the OR gate for the following inputs A and B given in the figure, okay. So, note the following. So, what happens when t is less than t1. So, please look at this scenario here. So, let us look at only this waveform here. So, if t is less than t1, A is 0, quite evident, you can see it is at the downward position, and B is also at a downward position, correct, because you can see a pulse being formed at the forward position. So, we can say that B is also at 0. So, if A is 0 and B is 0 and we are passing it through an OR gate, what will happen? The output will be 0. Let us look at T1 to T2. What will happen at T1 to T2? A is 1, B is 0. So, answer will be 1. So, it just moved forward, correct. T2 to T3, let us look at this location here. What is A? A is 1. What is B? B is also 1, hence Y will be 1. So, it is just simple straight line moving forward again. Next let us say T3 to T4. So, A will be 0 here, B will be 1 here. So, this will be again 1 here. For T4 to T5, let us look at T4 to T5 now. So, A will be 0 here, B will also be 0 here, hence it will pulse will go up, come down, and it will be 0 here. So, as you can see, Y is 0. Next thing is for T5 to T6, A will be 1 here, then b will be 0 here and y will be 1 here, fine. So, that is T5 to T6, that is y is 1, and finally, what will happen after T6, a will be 0 here, b will be 1 here. So, therefore, y will be 1. So, that is how you can understand the output waveform being formed depending upon the input signals or input waveforms, fine. Okay. That being said, so now we have understood what is a NOT gate. It is highly recommended to you, so that whenever you are studying these NOT gates and OR gates, you should also remember the diagram which is used upon here, because in some case scenario in exams only the diagrams will be input there, and we need to understand from the diagram that it is a NOT gate or an OR gate or an AND gate, etc. Okay. So, this is a NOT gate and this is an OR gate. Moving on to the next thing is your AND gate. So, an AND gate has 2 or more inputs, again as you can see it is having 2 or more inputs and only one output. Okay. How it is different? So, the output y of AND gate is 1 only. So, as you can see that it is 1 only and only when both are 1. If either of them are 1, it is not 1, it is only and only 1 when you need or you require or you have both input signals as 1. The logic symbol and the truth table for this gate are given in the figure. So, basically as you can see, if both are 0, 0, if again we got 1 0, so it is again 0, again we got 1 0, so it is again 0, but if both are 1, we got the answer as 1. So, that is how a truth table is formed for the AND gate, fine. Now, let us do a example for this question also. So, for this gate also. So, take A and B input waveforms similar to that in example 14.11 and sketch the output waveform obtained from the AND gate. So, as you can see from for t less than t1. So, what will happen for t less than t1? Oh, I think the complete diagram is not here. Okay, we need to just take the diagram same as this before. Okay. So, this is the same diagram which is being used there. I could not copy, but you can understand from at least this only. So, if A 0, B 0, Y 0, if A was, so even if you find 1 0, the answer will be 0 only. So, you can see y 0, y 0, here as both are 1, you will get the answer as 1, then again 0 0, so it will be 0 0 only, again 0, again 0. So, as you can see complete thing is 0, it is only 1 only and only when both are 1. So, as you can see for only a single time frame, that is between T2 to T3, we got the answer of the output as 1, rest every time it is 0 only, fine. So, based on the above, the output waveform for AND gate can be drawn as given below, fine. That means, so now till now we have understood what is a NOT gate, we have understood what is an OR gate, we have understood what is an AND gate. Okay. Moving to the next position, we will understand what is NAND gate. So, NAND, as you can see from the wordings only, and N is added to the AND gate. So, what it is basically, it is a NOT of the AND, it is basically NOT of AND. What does it mean? Let us first draw a truth table for AND. So, if 0 0, so it is 0, if 0 1, so it is 0, it is 1 0, so it is 0, and if 1 1, so it is 1. Okay. Let us suppose after this signal, after this output signal, we added a NOT gate. So, what will happen? This will be 1, this will be 1, this will be 1, this will be 0, and what if I say that this is the, what if I say that we just need remove this, and this is the truth table which we get for NAND gate. Okay. So, if either of them is 0, you will get the answer as 1, but if both of them are 1, you will get the answer as 0, and that is how the truth table of NAND gate is formed. Okay. So, you do not even remember this, just remember the AND gate truth table and you can directly approach NAND gate questions, fine. But one thing is required, you just need to remember the symbol for NAND gate. Okay. So, this is the symbol for AND gate, if a circle is being added upon here, then that is how a NAND gate is being formed. Okay. Fine. So, this is an AND gate followed by a NOT gate. So, please remember AND gate is first, then a NOT gate is there. It is not in the opposite scenario, as a NOT gate is not first, and first of all the input signals will be passed through an AND gate and then it will move on to a NOT gate. Okay. So, the inputs A and B are both 1, the output is not 1, quite evident, you can see from here also. The gate gets its name from this NOT AND behavior. So, figure shows the symbol and the truth table of NAND gate. NAND gates are also called as universal gates. Since by using these gates you can realize other basic gates like OR, NAND, and NOT. Fine. So, now let us simple same question for this also. So, again let me explain from here only. So, if t is less than t1, what will happen? A, so this is basically t1, t2, t3, t4, t5 and t6. Okay. So, for t less than t1, as you can see, A is 1, B is also 1, that means the answer will be 0, because if both are 1 then the answer will be 0. Similarly, from t1 to t2, A will be 0, B will be 0, Y is 1, then A 0 again, B is 1, so again Y is 1, then A1, as you can see a pulse is being uplifted in the A input, B is 0 only, so our answer is again 1, then A is 1, B is 1, then Y is 0, and then if A is 0, B is 0, then Y is 1. You should remember this, then when both inputs are 0, then the Y will be 0 1. And for t greater than t6, what will happen? A is 0, B is 1, so Y will be 1. Okay. So, that is how a NAND gate is being formed. Okay. Moving to the NOR gate. Okay. So, again understand this concept using same concept which you understood AND. So, what is basically AND? Sorry, what is basically NAND? N added to an AND gate. So, what will be NOR? NOR will be basically N added to an OR gate. Let us first make a truth table for OR gate. So, let us suppose if this is A, this is B and this is Y. We know that for OR gate to happen, if both of them are 0, it will be 0, but if either of them is 1, then the answer is 1. Let us try to add a NOT gate after this and write, let us say the output is Y dash. So, this will be 1, 0, 0, 0. So, what does it basically mean? That the answer is only and only 1 when both of them are 0. Okay. So, you can understand what is the difference between NAND, NOR, OR and AND. Fine. So, it has 2 or more inputs and 1 output. A NOT operation applied after OR gate, again very important that a NOT operation is basically, first of all OR gate is being added, that a NOT gate is added. NOT gate cannot be before an OR gate. So, a NOT operation applied after OR gate gives a NOT OR gate or simply NOR gate. If the output Y is 1, sorry, its output Y is 1 only when both inputs A and B are 0, that is neither one input nor the other is 1. Okay. So, it is only and only 1 if both are 0, neither one input nor the other is 1. The symbol and the please remember again. So, if you remember just this circle here, this is a OR gate symbol, and if you add a circle here, and this will be a NOR gate symbol. So, the symbol and the truth table for NOR gate is given in the figure. NOR gates are considered as universal gates because you can obtain all the gates like AND, OR, NOT by using only NOR gates. Okay. So, that is how the implementation is done, and that is all the 5 logic gates which you need to remember. Okay. So, we started with the NOT gate, then we went to OR gate, then we went to AND gate, then we went to NAND gate, and then we went to finally NOR gate. Okay. Please remember truth tables of them, or not remembering, just understand the logic, because understanding the logic is very important here. Okay. Fine. So, that thing being said, let me stop the discussion here only. In the last class of this lecture, I will move on with the integrated circuits, a small summary of the complete things which we understood in the previous all the 10 lectures or 11 lectures, and then we can close this complete lecture. So, let me stop it here only. So, thank you so much.